Hey chemists, how you going? This video is focused on triglycerides. So looking at organic chemistry, and this is one of the subtopics. So triglycerides as molecules are they form the basis of all oils and fats, and they're referred to as triesters. And this is because they contain three ester functional groups. So to form a triglyceride or a triester, you need a glycerol molecule and you need fatty acid molecules. So glycerol is propan 1,2,3 triol. So it has three alcohol functional groups. It has to be this exact molecule here. Okay. So glycerol is the more common name, and propan 1,2,3 triol is the systematic nomenclature. 3 fatty acids are required, and fatty acids are long straight chain carboxylic acids. So essentially this specific alcohol and 3 long carboxylic acids will combine to make a triglyceride or a triester. And obviously the word tri, the prefix at the front, means 3. So you have 3 branches coming off. So fatty acids are carboxylic acids that have long hydrocarbon chains, are unbranched, which means they're just straight chains. They don't have any other functional groups branching off, any substituents. They contain even numbers of carbon atoms between 12 and 20, and they're saturated or unsaturated. So saturation is referred to as if you've only got single bonds between the carbons. So think S for single bonds and S for saturation. Unsaturated means you've got carbon-carbon double bonds, so alkene functional groups, or triple bonds, alkyne functional groups. The saturation of carboxylic acids affects their cooking and storage properties and their health as well. Okay, so these are obviously found in foods, and they can vary in length, which affects their absorption, so how well they, I guess, are absorbed by the body, and how they're distributed around the body as well. So a few different examples. Here's a saturated fatty acid. So remember, carboxylic acid functional group, and you've got a straight chain hydrocarbon. Saturated means only single bonds. Here's a monounsaturated fatty acid. So you may have heard of monounsaturated and polyunsaturated fats before. So this is what we're referring to there. So here you've got one carbon-carbon double bond. So the molecule is referred to as unsaturated, and it's monounsaturated because you've got one alkene. And polyunsaturated essentially means you have more than one. So there's no ditri when we're really referring to this. So fatty acids as molecules can be saturated or unsaturated, and then unsaturated you can have mono and polyunsaturated fats. So triglycerides or triesters are edible oils and fats from plants and animals. Naturally occurring triglycerides nearly always consist of 3 different fatty acids. So what we mean by that is the chains that combine with the glycerol molecule are almost always different, just like this one here. So this is natural fish oil. It's a triglyceride, and you've got 3 different types of fatty acids. So this one here is a saturated fatty acid. This one here is monounsaturated, and this one here is polyunsaturated. So if you're referring to this triglyceride in general, you wouldn't be referring too much to its saturation because you've got different types of saturation from the fatty acids. So how are they formed? Essentially, your glycerol molecule is here. Your fatty acids are here. So we've simplified the large chain of the fatty acids with these R groups. And notice that you've got R dash and R double dash, which indicates that they're different. And you have, just like we've looked at with other reactions previously in organic chemistry, you have what's called a condensation reaction, where water molecule will fall off. Because there's 3 reactions happening here, you have 3 water molecules being formed. So this is what you end up getting, and you get that water molecule as well. So a pretty common question you have to look at is to draw the triglyceride formed from these fatty acids. Now when you're doing these types of questions, because the molecules are quite long, just be careful that you're counting up the number of carbons and double check that, make sure that it's correct. So this one here, we've got stearic acid, linoleic acid, and palmitic acid. So what would you do? Remember, the reaction occurs here, okay? So it's the OH that's coming off, and then this connects with the glycerol molecule in order to make an ester. Now, usually when you would draw this, I mean, the way I would draw it is left to right. So I would have this orientation, and I would basically flip this top one. So I'd have that coming around here, okay? And there's a few examples of this in your textbook to look at. Just one tip, triglycerides can be drawn as skeletal or partially condensed structural. So this is skeletal. What I would do is I would probably just keep the form that's in the question. So if these were given to you like this, I'd keep them as skeletal. I wouldn't change it because that change in form may lead to some errors. You just want to reduce the chance of making errors. So hydrolysis of triglycerides is when you break them up. So just like other reactions where you can get condensation reactions, you can reverse them by hydrolysis. And hydrolysis can occur in acidic or alkaline solutions. They occur inside cells of living organisms. So basically it breaks them down in order to get the energy within. This hydrolysis is catalyzed by enzymes called lipases. Triglycerides are referred to as lipids, so large non-polar molecules. So lipases are in saliva and in digestive secretions. So basically, your saliva can start breaking down triglycerides to aid digestion. So with your triglyceride, you can break it down into glycerol and fatty acids. Just remembering that in acidic conditions, you'll get fatty acids, but in basic conditions, you'll get the carboxylate ion for your fatty acids. So this is acidic hydrolysis, your triglyceride. So look at the ester functional group here, and you chop that up, just like when we looked at the ester subtopic as well. So this is no different. Chop it up, and then what you end up with is your alcohol and your carboxylic acid. Okay, so basically that there turns into this plus this as well. Just remember that obviously you get 3 different fatty acid molecules being formed, and those R groups may be different depending on what it looks like. Okay, for the reaction conditions, you usually put an acid up the top. So here we've just shown that it's in acidic conditions. Alkaline hydrolysis, same thing, except what you end up getting is instead of a carboxylic acid, you get the carboxylate ion, just like when we looked at the carboxylic acid subtopic there. So notice the formula for saturated fatty acids. So fatty acids, you have the formula of CnH2n plus 1 COOH. So again, what we've looked at in the carboxylic acids topic as well. So an example question, is the following fatty acid saturated or unsaturated? Okay, so we get given a formula here. So if we look at the formula CnH2n plus 1 COOH, essentially what we're looking at here is carbons, double them and add 1. So carbon 17, double that 34, add 1, 35. So I'd be expecting this to be 35 instead of 29. So the fact that there's less hydrogens means that there's double bonds, okay? How many double bonds? 35 take 29 is 6, and every double bond that's formed, you lose 2 hydrogens. So essentially, you end up having 3 double bonds, okay? So this is just the reasoning for that. The molecular geometry around the carbon atom. So this is probably just more for discussion rather than anything that you might be assessed on. The molecular geometry around a carbon atom is tetrahedral. So basically here you've got carbons coming off of the side and then one going up and one going out the back of the page for hydrogens, okay? But here for the double bond you have planar molecular geometry, which basically means it's flat, okay? So planar means on one plane, so flat, and tetrahedral means you've got something sticking out, so it's more a 3D representation. So bromine and iodine number. So this is a way that we can determine the saturation of triglycerides or fatty acids. With a double bond, you can have addition reactions with halogens. So bromine and iodine is a very common way to do this because bromine solution is a distinct brown color, and when it is added on to an alkene, it decolorizes. Same with iodine. So we can determine the number of carbon-carbon double bonds in a molecule. Bromine number or iodine number is the number of grams of bromine or iodine that will be consumed in a reaction with 100 grams of the alkene. So to start with this type of concept, you want to remember that 1 mole of bromine or iodine will react with 1 mole of double bonds. So an example question, you have this fatty acid here, and we can see it's got 2 double bonds, but we wouldn't know that if we were testing in the lab. So this is called linoleic acid, and it has a molecular weight of 281 grams per mole, and it has the chemical formula here. So you get shown that there's 2 double bonds. Determine the iodine number of linoleic acid. So how many double bonds does it have? It's got 2. So we can say it has 2 moles of double bonds, because 1 mole of linoleic acid would have 2 moles of double bonds, because every molecule has 2 double bonds in it. So linoleic acid has a molecular weight of 281 grams per mole, and it has the formula. So if we know that 2 moles of iodine will react with 2 moles of double bonds, we can say the mass of iodine required to react would be 2 moles, because we've got 2 moles of double bonds, multiplied by the molecular mass of iodine, which is 126.9 grams per mole. So essentially 507.6 grams of iodine would react with the linoleic acid. So the mass of iodine that reacts with linoleic acid is 507.2 grams. And the mass of linoleic acid is 281 grams, as there's 1 mole of it, as stated here. Now, do we remember what iodine number was? Iodine number was the mass that reacts with 100 grams of the alkene. So at this stage, this much iodine would react with this much linoleic acid. So what we end up with is a ratio. And what we're doing is basically we're saying if 506 grams of iodine reacts with 200 grams of linoleic acid, or 281 grams of linoleic acid, and then we're saying X grams of iodine, so we're trying to figure out the iodine number, reacts with 100 grams of linoleic acid. So basically we're making a ratio. We're saying this much iodine equals this much of linoleic acid. So this much iodine equals this much linoleic acid. Okay? Now, but it doesn't matter whether you do, which order you do this. So you could say 507.6 over X equals 281 over 100, or you could reverse it. You could say X over 507.6 equals 100 over 281. You're still going to get the same answer. Okay? So I'll show you how I would work that out. So if I go 507.6 grams of iodine equals 281 of linoleic acid over X grams of iodine equals 100 grams of linoleic acid. So basically we're trying to find X. We're trying to find how much of this reacts with 100 grams of this. So you would rearrange this algebraically. So in order to rearrange this, you would need to multiply both sides by X, okay, in order to remove X from the bottom here. So what you end up with is 507.6 equals 281 over 100 multiplied by X. And then you would rearrange by dividing both sides by this in order to get X by itself. So you'd end up with X equals 507.6 divided by, in brackets, 281 over 100. Okay. So what you end up getting, you should get 507.6 divided by, now I'm just going to do 281 over 100 in my head, because if you divide that by 100, it's going to be 2.81. Because I don't know how to use brackets on this calculator. So I get 180.64. Okay. Now the other way to do it, I'll just quickly show you this. We could do it the other way around. We could go X over 507.6 equals 100 over 281. And if I rearrange that algebraically, I would multiply both sides by 507.6. So this way ends up being a bit easier. 507.6 multiplied by 100 over 281. So I'll go 100 over 281 multiplied by 507.6, and I get the same answer. So X equals 181, which means the iodine number of linoleic acid is 181. So another question, calculate the number of carbon-carbon double bonds in linoleic acid given that 7.7 grams of I2 reacts with 2.8 grams of linoleic acid. So this is the opposite. We get given the iodine number and we need to figure out how many carbon-carbon double bonds there are. So 1 mole of iodine reacts with 1 mole of double bonds. So we need to calculate the number of moles of iodine and linoleic acid. So we need the molar mass for that. So the number of moles of iodine would be the mass that reacted, which is 7.7 grams, divided by the molar mass, which is 2 times 126.9. So you get that from the periodic table, obviously. And you get this many moles. So when you're comparing, you always have to convert to moles. Number of moles of linoleic acid, mass divided by molar mass. Remember, you get given the molar mass. No, you don't get given the molar mass, you get given the molecular formula. So you need to do 18 carbons multiplied by 12.81. So it's molecular weight plus 30 multiplied by 1.008 plus 2 multiplied by 16. And you get 0.010 mole. So you can see that this is 3 times the amount of this. Okay. So what does that mean? You had 3 times the number of moles of iodine for every 1 mole of linoleic acid. So remembering that 1 mole of iodine reacts with 1 mole of double bonds. So linoleic acid has 3 carbon-carbon double bonds. All right? Because it's that 3-to-1 ratio. And that's what it looks like, 1, 2, 3. So there's some more practice questions for you guys here. So here's another example. I won't go through this one 100%, but you have a fatty acid with molecular weight and an iodine number. How many double-double bonds? So the key thing is that an iodine number of 85 means 85 grams of iodine reacts with 100 grams of acid. So the knowledge of what iodine number actually means, how many grams of iodine reacting with 100 grams of the acid, is super important. So then you can figure out the number of moles of both the iodine required and the ricinoleic acid. You can see the ratio there is the same. How many double bonds? 1. So fats and oils are considered lipids, which are composed of triglycerides. They vary in appearance and functionality. Different types of fatty acid chains which join together form triglyceride molecules. They're not defined by a particular functional group. They're soluble in organic solvents, so non-polar, but not in water, which is polar. They contain non-polar carbon-carbon and carbon-hydrogen bonds and very few polar bonds, resulting in their water insolubility. So we know that water and oil doesn't mix, so this is just a summary of that. So the difference between fats and oils. Fats are saturated, so single carbon-carbon bonds. Oils are unsaturated. Fats are solid at 25 degrees Celsius. Oils are liquids at 25, so room temp. Fats are derived from land animals. Oils are derived from plants and small marine animals. Fats have higher density than oils. Fats have higher melting points than oils. So why are fats solid at room temperature? Why do they have high melting points and high densities? It's because of their structure. So saturated fatty acids are solids at room temperature. So think of butter. It's because the molecules compact closely together. So here's the fatty acid molecules. They kind of fit together really well. They have the same orientation tetrahedral, so the same molecular orientation around any carbon atom. So because they compact closer together, there's stronger London dispersion forces, which leads to higher melting point and density. Unsaturated fatty acids are liquids at room temperature. And this is because of that double bond. It provides a kink in the molecule. So this has planar molecular geometry. And what that means is it can't rotate and it can't move very much. It's kind of locked in place. So therefore, close packing of those molecules is not possible. There's differing orientations, as I mentioned earlier, from a central carbon here and an unsaturated carbon here. Therefore, there's weaker London dispersion forces experienced between chains, which leads to a lower melting point and density. So basically, if you've got unsaturation, it leads to kinks in the chain of fatty acids, which means they can't pack as closely together. So there's weaker dispersion forces experienced, which leads to a lower melting point and density because less energy is required in thermal energy to overcome. So here's an example of an unsaturated triglyceride that kinks in the molecule here, which means that the chains can't pack closely together. And here's a saturated triglyceride where it fits a lot more nicely together. So some fatty acid profiles of common oils and fats. So rapeseed oil, sunflower oil, olive oil, there's a whole bunch of them there. There's a bit of a breakdown between polyunsaturated, monounsaturated, and saturated fats. So those differences in percentages leads to the difference in chemical composition. And this is just to kind of show, that there is a difference between different oils, and they're made up of different types of fatty acids within those triglycerides. So this unsaturated triglyceride here, this has a monounsaturated, a saturated, and a polyunsaturated acid. So it's got 3 in 1 essentially. So oils can be converted into fats. So double bonds can be converted into single bonds. And this process is called hydrogenation. It's the addition of hydrogen under high pressure with high temperature and a nickel catalyst. So here's an example of an unsaturated triglyceride. So you can see those double bonds there, leading to kinks in those molecules. Hydrogenation, those double bonds will go away. So hydrogens get added on, which means the double bonds or the alkenes are no longer there. So micelles is basically the formation of lipids in order to get some action happen chemically. So just recall alkaline hydrolysis of triglycerides. So in alkaline conditions, you form a carboxylate anion. The carboxylate anion has a large non-polar carbon chain, and it has a small, very polar carboxyl group, which has a negative charge, so it can form ion-dipole interactions with water. So for this anion, the non-polar section is hydrophobic, so water-hating, and the polar anion is hydrophilic, so it's water-loving. So basically you've got different polarities in the one molecule. So what happens when you put this thing in water? It forms a structure called a micelle. Now micelles are nanoscopic, so they're very small, and what's happening is the hydrophilic head of the molecule, so this part here, loves being in contact with water. So they're going to form the outside of the micelle, or the border of the micelle. The hydrophobic carbon tails are water-hating, so they're going to try and kind of stick together, so they're in the center of this molecule. So basically the hydrophilic parts, or the hydrophilic heads, kind of shield the hydrophobic tails. So you get lots of these micelles forming. So here's a 3D representation where you can see that kind of protection from the hydrophobic non-polar carbon chain here. Now, the formation of micelles are quite useful in the body, or very useful in the body, and they can also be useful for scientists when we're looking at methods to deliver drugs, because a lot of the time drugs do not dissolve in water as well as we'd like. So these micelles can be kind of a transportation mechanism. So more than 60% of drugs are taken orally, and the micelle polymers can deliver them to a target site within the body, because basically drugs need to go to certain places within the body in order to act accordingly. So depending on where that is, we need, if the drug can't get to where it needs to go, it can be the most effective drug in the world, but it's not going to be as useful as we want. So the drug is stored within the core of the micelle, which is hydrophobic. So basically, if this is your micelle, this is the hydrophobic part, okay? The drug would be stored here. So the shell of the micelle is hydrophilic. It can dissolve in an aqueous medium, so blood, tissue fluid, so it can be transported around the body. Okay, so this is the hydrophilic part. The hydrophobic part here has the drug stored within it. Micelles are biodegradable, so they can be excreted without harmful effects. So this can be quite useful in that regard. So unimers are in equilibrium with micelle polymers. So basically, that's talking about how many there are. So an increasing concentration of unimers shift the equilibrium to the right-hand side. So the size and stability of the polymer micelles increases. Okay. So basically what that says is, if you've got these molecules that haven't formed a micelle yet, if we add more of them in the drug, then the equilibrium between the micelles and the unimers shifts towards the formation of micelles. So we get more of them, and therefore the stability of the polymer will increase, which is good, so the drug gets to where it needs to go. So another application of triglycerides is soaps. In order to make soaps, it's a chemical reaction called saponification. So saponification is alkaline hydrolysis of long-chain fatty acids, and it produces acid salts called soaps. So this is what we've looked at previously, except it's a specific base. So we've got sodium hydroxide here, which is a strong base. Heat it up, and you end up getting glycerol, and you get the sodium salt of a fatty acid. So it's not just the carboxylate ion, it's the sodium being added on as well. So a soap molecule looks like this. So it's basically a fatty acid, but it's the salt of a fatty acid. So this part here is the ionic salt part. So same deal as previously, hydrophobic, hydrophilic section. So the mechanism of soaps, the non-polar part of soaps dissolves in the grease layer. So you've got some stains on your clothing. So the non-polar part is going to basically adhere or stick to that stain, that grease stain. The ions will arrange around the grease droplet, and you'll get an ionic micelle being formed. So if you've got a shirt or cloth here and you've got grease, the micelles, the soap molecules arrange themselves like this to pretty much form a micelle. Okay. Now with agitation, so the movement in a washing machine or scrubbing, the dirt will lift off of the surface and the micelle will kind of be formed 100%. Now what happens here is the soap micelles repel each other because the ionic heads are negative and like charges will repel. So those micelles don't clump together, they spread out amongst the water, which is a good thing. Okay. So the running water forms ion dipole bonds and the grease is washed out. So essentially what happens is the micelles will form interactions with water. So you get lots of these micelles in the water with the kind of grease stuck in the middle. So the water gets dirty and then we can basically get rid of that water. Okay, and our clothes are clean. So just a few more representations of what that looks like. So the grease or oil droplet, the soap ions, which can be referred to as stearate ions, but soap ions is fine. And then you get the micelle being formed. And essentially, chemically, that is how soap works. Thanks, guys. I know it was a long video, but hopefully you've got your notes document filled in. And good luck with your triglycerides work.